So if you want to get the volume of a cone, it's just going to be something like the volume of a cylinder that has been split up into 3 separate parts, meaning that we have formula for a right cone, that is a cone with a right triangle vertical slice, as it were, is going to be 1/3 pi r squared h. Third of the cylinder, just like so, but that's not very interesting by itself. You've seen a couple of these formulas, so let's get one more here.
You think we need one more? You think we need one more? All right, we'll get one more.
With this, we can also talk about spheres, where spheres are in some sense combinations of our cones and cylinders in terms of where they end up being, that we have the volume is 4/3 pi r cubed. Because it's sort of like these graduated and, I guess and the opposite of graduated is additions of circles on top of each other to get these shapes, where obviously in the real world, perfect spheres are pretty rare, although less rare than perfectly flat things. But, well, this is what we're working with. We're kind of assuming a bit of a perfectly spherical world for the sake of keeping things accessible, I guess I'll say for now. If you want to get more oblong spheroids, well, that's a bit more advanced, a bit beyond what we're going to see at the moment. So, let's get some practice with how we can use these two formulas. For this example, we have that an ice cream cone is 5 inches deep and has a radius of 1 inch. A spherical scoop of ice cream also has a radius of 1 inch. If the ice cream melts into the cone, will it overflow? So, again, it's a little bit silly to assume that the cone has that perfect radius we want at the top there. And it's also a little bit silly to assume that the ice cream has that perfectly spherical behavior as well in terms of its maximum radius. It's probably going to be a little bit lumpy and not even like a perfect sphere when you scoop it out there. Anyone who's seen that sort of thing knows it has that weird sort of fluffy shape to it. But we're being simplistic because it's easier to do simple geometry than complicated geometry. And generally, people would rather live in a world where math is easy than a world where math is accurate. So let's stay in the easy world here and think about this, where our goal is to find out whether the volume of the scoop is bigger than the volume of the cone, because if it is, that means it'll overflow. You'll get ice cream all over your hands, and no one likes that. It makes your hands very sticky. It's inconvenient, so let's hope that doesn't happen even though it means less ice cream, which is itself kind of sad. But hey, I guess we'll take convenience over more ice cream. It doesn't seem right to me anymore, but we're going to work with it anyway. So, we need our two volumes here in terms of those shapes. We need the volume of the cone, which I'm going to call VC, as well as the volume of the sphere, which I'll call VS. Where for VC, volume of cone, we're going to use that formula there. Pi, our radius r is 1, that's getting squared, and our height here is 5. So what we're going to end up with in this case is, oh, and importantly, a 1/3, well, 5/3 pi cubic inches, where pi is 3.1415 and then so on. So we'll say that pi is about 3. That means our volume in this case, canceling out the pi with the 3, is about 5 cubic inches of cone to work with. Meanwhile, for the spherical scoop there, Vs, we have 4/3 times pi times the radius here cubed, but it doesn't really matter that we're cubing the radius in this case because we're just cubing a 1. It doesn't really do anything. So we're going to end up with here is going to be 4/3 pi inches cubed, and using the same sort of approximation, that gives us a volume of about 4 cubic inches for the scoop, which means, hooray, we don't have sticky fingers. We have a big enough cone to fit the ice cream in there. So that's about all we have here for our basic volumes. Let's finish this section looking at the cousin, as it were, of volumes, surface areas.